Hello everyone, let us continue our discussion. We are in week 12 and this is our fifth lecture. As of now, we have studied buckling, right? And if you recall, we have estimated Euler's buckling load, right? So the expression of first critical buckling load is pi square EI divided by L effective square. Now, if you recall, we also defined slenderness ratio, that is lambda bar, right? This is L effective divided by least lateral dimension. Let us consider that to be B. Today, let us first take this definition of slenderness ratio and let us see how the column behaves under this action of a compressive load and for different values of lambda. Recall, we defined a limit lambda prime less than equal to 12 for short column, right? And if it is greater than 12, we call it long column. Now, before we move further, let me just clarify that this definition is for RC structure, and these limits are provided in IS 456 for RC columns which are primarily rectangular. So if you have a rectangular column where we have B and D, then we consider least lateral dimension, and using that least lateral dimension for the RC column, we first find out these two conditions, and accordingly we decide whether we deal with a short column or with a long column. Now for short column, obviously it fails due to crushing that we have already discussed, and for long column we have critical buckling load, right? Now these limits vary. So the value 12 you can see on your screen, it varies from one material to another material. Not only that, a better way to define slenderness ratio is L effective divided by R. R is the radius of gyration. So I, moment of inertia, is A times R square. So this expression we can further modify pi square E A times R square divided by L effective square, and then we ultimately get pi square EA divided by lambda bar square. Now for steel column, we use this definition of slenderness ratio where we consider radius of gyration R, right? And for steel column, the limits are lambda less than equal to 32, and that is short column, and if it is greater than 120, it is called long column, and in between this range 32 to 120 we call it intermediate column. Likewise, if we change the material, this limits may vary. Nevertheless, if you can remember these limits for two different material that mostly we deal with in civil engineering, one is reinforced concrete, another is steel. And for that, these limits are popular, and accordingly we can decide whether the column, that is a compressive member, fails under solely due to crushing or due to buckling. In reality, if you recall, in case of Euler's formula, we had some assumptions. Some of the assumptions doesn't hold in reality. For example, if we consider fully fixed ends, which may not always be fully fixed. Not only that, if you recall, at the very beginning, when we defined column, we applied the load along the central line of the column, right? Which also doesn't hold always, because when we apply load over a column, we may have some eccentricity from the central axis of the column. Now, due to these reasons, a column may fail under the combined action of crushing and buckling. And if you have recall that we have also defined Rankine's formula, right? So Rankine's load is 1 by R or 1 by P is equal to 1 by PC plus 1 by PCR. This we have learned in our previous lecture, and we solved some problem also how to quantify the Rankine's critical load. So pre-critical Rankine we can estimate, and where we have the combined effect of crushing and buckling. And if you recall, we derived the expression where we express this critical load in terms of the crushing load, which is multiplied by a factor, and that factor deals with the effect of buckling, right? Now, today we are going to see if you have a column and then if there is an eccentricity between the line of action of the load and the central axis of the column, then how to deal with that problem. So let us draw a column. For example, say this is the column, and if we have a load which is acting say here, and the centroidal axis of the column is somewhere here, right? Then this line, the centroidal axis, has an eccentricity with the line of action of the force. So this is the eccentricity. So we have a load P. Obviously, we'll also have a load at the bottom, okay, and we apply appropriate boundary conditions, right? For the time being, let this boundary condition be hinge. So we have hinge here, and we also have a hinge there. We can change the boundary condition, so that's not an issue. Let us consider hinge at the ends. Now, our first task is to derive the governing equation along with its constants, which we know from our previous lecture. So let us try that, and for that let us first redraw the column as line element. So let this is column, and let us consider the eccentricity here. So we apply load P with eccentricity from the center line of the column. And we have a hinge support. So let us draw the hinge in a different way. So this is a hinge. Now let us identify the axis. So we have y-axis here, and we have along the center line of the column we have x-axis. Now this column is going to bend like this, and obviously the moment it bends, load line also bends, and we have the new location where the load shifts. And as usual, let us consider a section at a distance x from the origin. Now, the deformation here is y, and the moment at x, let that be mx. This moment is the load P. Earlier we had no eccentricity, so we multiplied this load with y, but right now we have eccentricity E plus y, and that is the lever arm. So if we multiply load with the lever arm, we get the moment acting at a distance x from the bottom end, right? Now the governing equation is, again we can easily write EI d2y dx2 is equal to minus m as per our notation. So therefore we have EI d2y dx2 is equal to minus p times E minus p times y. Then what we do? We take this p times y on the left hand side and rewrite this equation. So we have d2y dx2 plus lambda square y is equal to minus lambda square E, where lambda square is equal to P by EI. Now for this problem again we can write down the solution. Yx is, you can easily write C1 cos lambda x plus C2 sin lambda x. Then we have particular integral, that is E. So what we have to solve? The constant C1 and C2, and that we get from the boundary conditions, right? So we have boundary conditions which are at x equal to 0, y is also equal to 0, and at x equal to L, y is 0. So if we put the first condition, so we have y of 0 is equal to C1 cos lambda times 0 plus C2 sin lambda times 0 minus E is equal to 0. Obviously this term will go to 0 and we have C1 is equal to E. So we have the first constant C1 which is equal to the eccentricity that we have between the load P acting on the column and the central axis of the column. Now for the second condition, we have y of L is equal to C1 which is E cos of lambda L plus C2 sin of lambda L minus E is equal to 0. So let us solve this expression further. So we have y of L is equal to E cos of lambda L plus C2 sin of lambda L minus E is equal to 0. So what we get? We get C2 is equal to E. If we take E common, and first we take the right hand side, and then we have 1 minus cos of lambda L divided by sin lambda L. Now we can actually express this cos lambda L as cos twice of lambda L by 2. Similarly, sin lambda L as sin twice lambda L by 2. and further simplify this. So we'll get E, then 10 lambda L by 2. Right. So now we have both C1 and C2, and we can write C1 and C2 in the main equation and get the deformed shape. So we have C1, which is E cos lambda x, plus C2, which is E times tan lambda L by 2 sine lambda x and minus E. Of course, we can expand this and further simplify, but before that, let us first find out deformation y at x equal to L by 2. Because if you look at the configuration, at L by 2, we have the maximum deflection. So this is y max. And let us first find out the expression for y max, right? For that, we have E cos lambda L by 2 plus E tan lambda L by 2, then sine lambda L by 2 minus E. Okay. Now we'll simplify this expression in a minute. Before that, we take this E common, and what we have is cos lambda L by 2 plus tan lambda L by 2 times sine lambda L by 2. So we have sine square lambda L by 2 divided by cos lambda L by 2 minus 1. Then obviously if you simplify this further, we have cos square lambda L by 2 plus sine square lambda L by 2 in the numerator. So effectively we get E times sec lambda L by 2 minus 1, and that is the expression for maximum deformation. So this is y max, which is shown here. So we have the expression for maximum deformation at the center, and we can further simplify it. That we'll do in a minute. So we have y max is equal to E sec lambda L by 2 minus 1 and sec theta we can write it as an infinite series. So we have 1 plus theta square divided by twice 2 factorial plus 5 theta to the power 4 divided by 4 factorial and so on. So if you consider the first two terms, if the theta is small or p is small, that means we truncate this series and consider first two terms and rewrite this expression. What we have 1 plus, in our case theta is equal to lambda L by 2. So we have lambda square L square divided by 2 square times 2 factorial. So we have 8 and then minus 1, right? So this 1 will get cancelled and effectively we have lambda square L square E divided by 8. Okay, so now we can also evaluate the maximum moment, and for that again let us consider the deformed shape. So we have P, which is with the eccentricity E and obviously the maximum moment here at the middle is P times E plus Y, but Y is at the middle Y max, right? So the expression for maximum moment is P times E plus Y max. So effectively what we have? We have P times E sec lambda L by 2. So what we get is the expression for maximum bending moment, and also we have derived the deformed shape of the column when it has a eccentricity between the applied load P and its centroidal axis, right? Now for this column, let us find out what is the sigma max. So sigma max in this case is actually the stress caused by this force P, and we have cross-sectional area, say A. So P by A is the compressive stress, plus due to bending we have maximum moment at the middle, so M max divided by I times Y of the extreme fiber from the neutral axis, right? We know this expression for bending stress from our previous studies, right? Okay. Now we know section modulus, if you recall, is I by Y, right? So we can further simplify this expression. So we have M by Z. So let us now put the expression of M max in this equation and let us see what we get. So in case of M max, we have P times E times sec lambda L by 2 divided by Z. Now we know what is I. I is A times R square. R is the radius of gyration. So we can put the expression of lambda in this lambda L by 2, and if we do that, we have lambda equal to P by EI times L by 2. So in place of I, we can write P by E A R square times L by 2. And then ultimately we get L by twice R square root of P by EA. So now if we find out what is the expression for maximum stress for this column having some eccentricity E between the load and the centroidal axis, so we have P by A here, plus we have PE, and in place of lambda L by 2 we can write sec of L by twice R, then square root of P by EA. And we also have a Z here. Okay, so now if we take P by A common, so the first term we have 1 plus we have E, then A divided by Z sec of L by twice R square root of P by EA. Now if we look at this term, what is EA by Z, it is E A divided by, in place of Z, we have I by Y. So A R square divided by Y. So effectively we have E Y divided by R square. So you can replace this with E Y divided by R square. Now this Y, let me just put a bar here, because this is the distance of the extreme fiber from the neutral axis, and this is certainly not the Y here. Okay. Right. So let us just put a bar here so that we can differentiate between Y bar, which is the distance of the extreme fiber under bending from the neutral axis of the cross section. Right. Now, this formula, sigma max is equal to P by A within bracket 1 plus E times Y bar by R square sec within bracket L by twice R square root of P by EA. This is called secant formula. Now, in this expression, you see we have the combined effect of crushing, that is here, and bending, which leads to the first critical buckling load, right? And this expression here if you look at the dimension, it is dimensionless, so it is called eccentricity ratio. So we have two things to deal with. One is slenderness ratio, that is L by R, and we also have eccentricity ratio in the second form, right? Okay. Now, if we plot the stress versus lambda, and this is lambda bar, actually slenderness ratio. So we have, this is the Euler's equation or Euler's curve, and if we mark the sigma crushing, which is equal to P by A, this is here somewhere, and for this line we have Y bar times E divided by R square is equal to 0, and for non-zero values, if we plot, we get like this. So the values are, say, 1.0, then 0.8, 0.6, and ultimately we get this curve. Well, normally we draw the form line here, and beyond this actually the dotted line. Now if you look at the second expression, which is here, and in that expression, let me just write it again. So we have sigma max is equal to P by A within bracket 1 plus E y bar divided by r square sec L by twice r square root of P by EA. So the moment we have E equal to 0 in this expression, you see, there is no eccentricity, and the moment we have no eccentricity, second formula is no longer applicable, and we have PCR as per Euler buckling load that we have already discussed, right? Okay. Now let us consider a different case and see how we can derive the expression for deformed shape of a column which is cantilevered but having an eccentricity of E, right? So for that, let us consider this column, and for this column, the bottom is fixed because now we have a cantilever, and then at the top we have a eccentricity, and then we apply a load P. So this is the eccentricity E, and for that we have the deformed shape Now for this problem, again, let this deformation here be A. Obviously, what is the moment acting? If we consider a section at a distance x from the bottom, so this is say y, so M is equal to P times the lever arm. In this case, the lever arm is A plus E minus Y. So now again we can write down the governing equation. So it is EI d2y dx2 is equal to minus P times A plus E minus Y, but the moment is, it is a hogging moment, so it is actually negative, so we have positive here. Now if we further simplify, we have EI d2y dx2 plus P times Y is equal to P times A plus E. Then we have d2y dx2 plus lambda square y is equal to lambda square A plus E. So lambda square is equal to P by EI. Now the solution for this differential equation is C1 cos of lambda x plus C2 sine of lambda x plus A plus E. Then what we do, we again apply boundary condition. So BCs are at x equal to 0, y is 0, and at x equal to 0, y prime is also equal to 0. So if we apply the first boundary condition, we have 0 is equal to C1 cos of lambda times 0 plus C2 sine of lambda times 0 plus a plus e. So effectively we have C1 is equal to minus a plus e. Now for the second boundary condition, let us first differentiate the expression. So the deformed shape y of x is C1 cos lambda x plus C2 sin lambda x plus a plus e. So y prime of x is equal to minus C1 lambda sin lambda x plus C2 lambda cos lambda x. So if we put the second boundary condition, which says y prime of 0 is equal to 0, so we have minus C1 lambda sin lambda times 0 plus C2 lambda cos lambda times 0, which is equal to 0, and therefore C2 is equal to 0. So y of x is equal to C1, which is minus a plus e times cos of lambda x plus C2 is 0, so the remaining term is a plus e. So what we have, a plus e times 1 minus cos of lambda x. So that is the equation of the deformed shape when we have fixed free boundary condition, right? Now, what is lambda? Lambda is equal to square root of p by ei, and we have one more condition to satisfy. So at x equal to L, the length of the column is L and flexural rigidity is ei. So at x equal to L, we have the deformation which is A. So at x equal to L, we have y of L is A is equal to a plus e within bracket 1 minus cos of square root of p by ei times L. So if you simplify this equation, you can show that A is equal to E times sec square root of P by EI L times minus 1. Right. So we get the expression of maximum deformation at the top, that is at x equal to L, and then now we can find out what is the maximum moment. So maximum moment Mmax is equal to what? Again, if we go back to the actual configuration, so we have a moment here, and that moment is nothing but P times, that is the load, times A plus E. So we have already derived the expression for A, and if you see, A is equal to E times sec of this first bracketed term minus 1. So if we take 1e on the left hand side, we have a plus e, and that is equal to sec of square root of p by ei times L. And obviously, the moment we open this third bracket, we have e multiplied by this sec of first bracketed term. So we'll have a e here. Right. Now if we write down the second formula, we have sigma max is equal to p by a plus a max, that is p times e sec square root of p by ei times L divided by I times y bar. Again, this y bar is the distance of the extreme compression fiber from the neutral axis, right? So we can further modify this expression. We have p by a common, then within bracket we have first 1, then plus we have e times y bar divided by r square sec square root of p by ei times L. So again we get the expression for second formula corresponding to the maximum sigma max, and this quantity here is called the eccentricity ratio as we defined earlier. So this is a non-dimensional number, and we get the maximum stress developed in the column when we consider both crushing and buckling. Right. So let us stop here. What we'll do, we'll solve some problem in the next class, and then we'll further extend this buckling problem when we'll have a longitudinal load, and that we'll see how to solve in the next class. Thank you very much.